use some notation that you're definitely familiar with. So let's start with a topological space xt, and let's say A is an element of X. Okay, so we're starting with a set X that is not empty. We're defining a topology on it. It's a collection of subsets of X satisfying the properties that we talked about, and we're taking an element. We're taking a subset of X, excuse me, and we're trying to define some terminology here. We're gonna define the interior of A to be, it can also be written like A superscript 0. This is called the interior or circle. It's called the interior of A. And what it is it's like the union of all open sets contained in A. So if we want to write it in terminology, we can say it's the union of all the sets U that are contained in A and open, and I'm unioning all of these U's. Okay, so this is the interior of a set A, and we're gonna define the closure of A to be the intersection of all the sets V that are closed, right? So there's gonna be all the sets V that are in A that are it's gonna be all the sets V containing A. So A is gonna be contained in V, and V is gonna be closed. Okay, one more time. Let's talk about this. The U's here, these U's are elements of T. So what are we saying here? We're saying that the interior of A, it's the union of all elements of the topology T that sits in A. Okay, so we have the set A. It is an X. It of course contains some elements of T, at least the empty set. And we're saying what we're gonna do is we're gonna union up all the elements of T that fall in A, and we're gonna call that the interior. In other words, the union of all open sets in A. It's gonna be the interior. And it's trivial here that the interior will be contained in A, because each U is contained in A. For the closure, which is A bar, what we're gonna do is we're gonna take all closed sets V or closed sets V containing A, and we're gonna intersect them. Okay, and if we intersect all of these closed sets, we're gonna end up with the closure of A. And it's important to notice here that the sets V, what are these? These are complements of elements in T. In other words, it's closed if and only if its complement is open, as usual. Okay. Two important notes here. The interior of a set, it's gonna be the largest open set contained in A, right? So this is an important thing to observe. Since I'm unioning up all the open sets in A, then this is gonna be the largest open set in A. Of course, why is that? It's because if you give me an open set and you claim that it's the biggest one, then it's definitely contained here, right? So if you start with any open set in A, then it's definitely contained here. So any open in A is contained here. So it's the largest. And the closure, it's the smallest closed set containing A. And why is that? It's because if I take any closed set containing A, let's say V prime, it's a closed set containing A, then V prime is one of these sets here, right? It's a set containing A and it's closed. So V prime, it's among these sets that I'm like intersecting, right? But if I take V prime and I intersect it with something else, then I'm gonna definitely get something smaller. So it's always the case that we have this. And hence, this set here, it's the smallest closed set containing A, okay? And it contains A because each and every one of them does. Okay. So that's important to observe, and these definitions are very important and can be used in proofs. So please make sure that you also remember that. All right, some other terminology, the boundary, this is called the boundary, by the way. The boundary is going to be the closure minus the interior. So if we take the closure of a set and we subtract its interior, we're going to get the boundary of the set. As an example, in metric spaces, for example, or in the Euclidean space, if I look at the disk, its boundary is going to be just, the circumference. This is going to be the boundary of the set, and the interior is going to be whatever is inside that. All right. So one more or a few more terminology here. We're going to say A is dense if its closure is the whole thing. And we're going to see, we're going to be talking about dense sets as we go. But I'm just introducing these definitions. So A is a dense set if its closure is equal to X, right? If its closure equals the full space, then it is dense. And we're going to see that these are very important sets. Okay? We're going to say A is nowhere dense if the interior of its closure is empty, right? So in other words, if I start with a set A and I look at the smallest closed set containing A, so I'm going to start with a set A, take the smallest closed set containing A, let's call it, I don't know, it's A bar in this case. Then if the interior of that closure, if the largest open set contained in that closure is empty, like there's no interior of the closure, then we're gonna call it nowhere dense. Such sets exist, and we're gonna see some examples later on. But it's important to keep these definitions in mind. All right, two important things I want to note before we continue here and see a proposition, prove it, and end this video. Are these two two nice properties. If you start with the interior of the set A and you take its complement, you will end up with the closure of the complement. And if you start with the closure of the set and you complement it, then you'll end up with the interior of the complement like this. Okay. So the reason I'm mentioning these is because I want to note that if you want to do this in the usual element-wise proof, you take an element here and you prove it here, and then you take an element here and you prove it here, it's gonna take you some time, right, to do it, though it's not hard. But there is literally a proof. So in other words, let me just write it this way. I'm gonna prove just the top one, and the bottom one is similar. So what is the interior of A? It's the union of all open sets U contained in A And what I'm doing is I'm taking the complement of that. So I'm gonna end up with the intersection of the union, the intersection of the U's, where the U's are the open sets of A, like this. Then we want to show that this is the same as this thing. So maybe let's write that here. Let's write that here. So what is a complement closure? By definition, the closure, it's the smallest closed set containing a complement. In other words, it's the intersection of all the V's contained in a complement such that V is closed. Yeah. And thus, what is that? This is the same as we want to show that this thing and this thing are the same. Well, that's clear. Why is that? I mean, look at it. It's like we're doing a quote-unquote a change of variable here. All right, so now that we've introduced these notations, we need two more we need two more definitions before we prove an important proposition here, which are the notion of a limit point and the notion of a neighborhood. So let me just there are multiple ways of defining these. Some people call them accumulation points or cluster points. I like to call them limit points, to be honest. It's more familiar, this notation. So an element x of x is said to be a limit point if and only if I take any neighborhood. Oh, I should probably tell you what a neighborhood is first. Okay, so a neighborhood of x is just a set that contains x in its interior. So you can take it as a definition. U is a neighborhood of x in x if and only if x is in the interior of U. So we're gonna say x is a limit point if I take any neighborhood of x and I intersect it with. So if I take any neighborhood of x and I take out x and then intersect it with a, this shouldn't be empty. So what are we saying here? We're saying that every, like, the way you can remember it is deleted neighborhoods of limit points must contain at least one point. So we have this space x, okay? We have this point in it, and we have a neighborhood. And what we're saying is, or maybe let's do it this way. Yeah, that's fine. We have a neighborhood here, U. What we're saying is, if I intersect U with A, I should get at least one point other than X. I figured to make this, you might have heard this, you might have seen this definition before, but just to make sure that we're all on the same page, maybe let me give you an example. So let's take the real numbers, for example, and maybe let's contrast boundary points and limit points. So let's take this example. If we take the real numbers with the usual topology, meaning you can think of the usual way of defining open sets in R. You're taking open intervals to be open sets and their unions. And let's look at the point, for example, 0. Let's take the set containing 0 only, okay? And containing nothing else. So if we take the set A to be just 0, what can we say about 0? Is it a limit point? Is it a boundary point? What is it exactly? So we will see, you can see here, for example, that 0 is not a limit point. 0 is not a limit point of A. And why is that? It's because if I take any neighborhood of 0, if I take U in R, neighborhood of 0, for example, think about an open interval about 0, then if I take 0 out of U and I intersect it with A, A contains only 0, so there are no other elements, so this is empty. And this is bad, right? So this is bad because it contradicts the definition of limit or accumulation points. So 0 is not a limit point. So you can see, however, that 0 is a boundary point. Why is it a boundary point? So maybe it's important to remind you of the definition of boundary points here. So X is in del A, like it's a boundary point of A, if and only if you take any neighborhood of X, then that neighborhood must intersect A, and it must intersect the complement of A. So let me just show you what I mean here on a picture. So if I have this disk, we usually used to say that elements here are boundary points, or you might have heard that these elements are boundary points, and the reason is, if I take any neighborhood that point, if I take, for example, any open ball about that point, around that point, then it must intersect the inside of the disk and the outside of it. So in that case, we say, for example, that this point is a boundary point of the disk, right? In this sense. So there are two ways to see boundary points. You can either use this definition that they must belong to this set defined as such, or you can use the definition, which is equivalent, of course. You can use the definition that every like a boundary point is a point where every neighborhood of that point must intersect the set and the complement of that set, right? Notice there's a very important distinction here for accumulation or limit points. We're requiring that the deleted neighborhood intersects A. But here, like, we're not requiring that the deleted neighborhood intersects A, just the neighborhood. Okay. And I invite you to think about what happens, or when these possibly might coincide, or one of them might be the other. Think about isolated points, and you'll see what I'm talking about. Okay. Let me just give you another example here. Let's look at the set, for example, 0, 1, and let's look at the point 1/3, for example. So 1/3 is an A. Is it a boundary point or a limit point? Well, it's not a boundary point. And the reason is this is not a boundary point. And the reason is I can take the neighborhood, for example, I can take the neighborhood 1/4 till 1/2. So this belongs, or this is an A. It's a neighborhood of 1/3. It's an open set, in this case containing 1/3. It's a neighborhood of it. And moreover, it doesn't intersect. This is a neighborhood. This is our U. It's like it indeed intersects A because it is an A, but it doesn't intersect the complement of A. U intersected with A complement is empty. So we just contradicted this definition that it must be it must be the case for every neighborhood that it intersects the set and its complement. But we could violate this, so 1/3 isn't a boundary point. 1/3 is an interior point, however, and you can also see in this case that 1/3 it's a limit point. Why is it a limit point? Well, because if I take any neighborhood, U, if I take any neighborhood U, whatever it is, let's say this is the U. So any neighborhood U, of course, is gonna contain an open interval around 1/3. So if I take any neighborhood U of 1/3, it must intersect the set 0, 1 at points other than 1/3, right? So if I look at the deleted neighborhood, if I take out, so if this is U and I take out 1/3 of it, then it's gonna still intersect 0, 1. Okay, so leave it for you to fill in the gaps here, the details. But these are some examples and some important distinctions. Okay, so we're gonna wrap up this video by an important fact that we're gonna prove quickly, which is this fact. So if we define the set of accumulation points, so if we start with a topological space, and we say, let's say A is an X, we're gonna define the accumulation set of points of A to be, of course, all the points in A such that X is a limit point or an accumulation point. Okay, and we want to prove this fact about limit points, which is the following. We want to show that the closure of A can be decomposed into the set A and the set of limit points of A. So if I take any set A and I union with it its limit points, then I get the closure of A. This is a very important identity here that we're going to be using. So we're going to prove it quickly. And more importantly, a set is closed if and only if it contains all of its limit points. So a set A is closed if and only if all of its limit points belong to it. Okay? So we're gonna see, for example, proving this isn't that bad. It's quick and easy. So maybe let's go over the proof quickly. So let's start by showing this identity, this equality, and we're gonna show it in the element-wise sense. So we want to show that if X is here, then X is here, and if X is here, then X is here. So showing this is the same thing as showing X in A bar if and only if X is in A union A, the accumulation set of A. Let me just use a different notation here. So this is the same as same as showing this, but this is the same as showing X is not in A bar if and only if X is not in A union the accumulation set of A. So in other words, I'm gonna show this by showing this, because these are the same thing, right? Okay, so let's see how to show this. For example, if we start with the left hand side and we want to show that X, if we start with X that is not in the closure of A, we want to show that it's not in this union. Well, that's trivial. We automatically have that X is not in A, and of course, if we look at this, what does this mean? So let me just write it this way: X is in the complement of this. This is open, but since it's open, then I can find a neighborhood or an open set around X that is contained in it. So maybe we can show it this way: X is not an A, and there exists U open such that maybe we need some more space here. So let me continue it. Here. What do we have so far? We have that X is not an A, and we're just trying to show that X is not an accumulation point of A. But what is an accumulation point of A? X is an accumulation point of A. X is an accumulation point of A if and only if every deleted neighborhood of X is gonna intersect A, right? But notice, since this is an open set, then it is automatically a neighborhood of X, and it doesn't intersect A, right? This is a neighborhood of X, and the deleted neighborhood, this thing intersected with A, is clearly empty, right? Because this thing contains A, right? It contains A. So this clearly implies that X is not in this union, because it's in neither, then it's not in the union. And showing the other direction is also easy, and you can see it by saying, well, if X is not in A union the accumulation point of A, then what do we have here? Then we have that X is in the intersection of this complement, the union of this complement, and thus it's thus what do we have? We have that X is in A complement intersected with the accumulation point set of A complement, and then X is this is the same as saying X is in A complement and X is in the accumulation set of A complement. So X is not an A, and X is not a limit point of A, and we want to show that this implies that X is not an element of the closure. The closure is A union the boundary set of A, or the interior union the boundary set of A. But thus it suffices to show that it's not a boundary point of A. Why is that so? That is because of the definition of limit points. This thing means X is not a limit point, right? But X is not a limit point. This is the same thing as saying that there is a neighborhood that violates the property needed to be a limit point, right? Violates this property that every neighborhood must have the property that if you delete x from it, it still intersects A. But what does that mean? This means that there is a neighborhood where if I delete x from it, I don't intersect A. In other words, this is the same as saying that there is a neighborhood of x such that it's entirely, well, first of all, it's contained like this in a complement, but x is not in, but x itself is an A complement. So we have x is an A complement and this thing is an A complement. Then what do we have? We have that u is entirely an A complement. So there exists u neighborhood of x such that it's entirely an A complement. But this, of course, violates the property that x is a boundary point. So in this case, so let me write it this way here. We have this so far, and this is the same thing as saying x is not in A bar. Why? Because x is not in A and x is not a boundary point. Why is it not a boundary point? Well, because if we have that there is a neighborhood of x that doesn't intersect A, then we literally just agreed that the definition of boundary points, a point is a boundary point if every neighborhood of it intersects A and the complement of A. But we just found a neighborhood that intersects only the complement of A and it doesn't intersect A, right? So it misses A. And since that is the case, then x is not a boundary point. And we already have that it's not an element of A, thus it's not an element of A bar, okay? So this finishes the proof of this equality. And this fact is now trivial if we want to show that A is closed if and only if the accumulation set of A is in A. In other words, A contains its limit points. That's clear because we can use this fact that A bar is equal to A union the accumulation set of A, and you can see that you can see, for example, this direction, A closed implies A is equal to A bar, and this implies of course from this identity by star that automatically the accumulation set of A is contained in A because the left hand side now is A, and if like the accumulation set of A is in A, then by star again I'm unioning something that is in A with A, then I'm gonna get A, right? So by star I have A bar is equal to A, and this means A is closed. Alright, so this finishes the proof of this proposition, and it's an important one. It's an important classification of like closed sets. So I use something here. I use that A is closed if and only if A is equal to A bar, but that's clear, that's trivial. In fact, A is open if and only if A is equal to the interior of A. And of course, this is trivial by the very definition of closure and interior, right? Um, because if A is up, so the interior, for example, is the largest open set in A, right? So A is gonna be open only if it is itself the largest open set contained in A, right? And if and only if, actually. And the same thing for the closure, right? A set is closed if and only if it is the smallest closed set containing itself, right? And that's clear.